Okay, well here we are at the next set of tutorials. This tutorial is going to deal with calculating descriptive statistics from numerical and categorical data. And you can follow along. I would advise you to follow along actually. You can find the file on the Blue Line site, week 03 tutorial, descriptive stats, demo data is what it should be called. And when you open your file, you will see that it looks something like this. We have two worksheets, a demo numeric and a demo categorical. We'll deal with the categorical when we get there. So if we look at the demo numeric data here, we have a column for x and y. We'll deal with x first, and then we'll look at some of the changes to some of these descriptive statistics that we're going to calculate when we alter the distribution of these values. So when you look here at this portion that's showing you these two different graphs, the bottom graph isn't going to do anything in the beginning until we get to y. And as you look here, you'll notice that this looks very familiar to what you saw last week when we were making histograms. As I note here, if you want for mean, median, and mode to magically appear on these plots, it has to go over here in this section. Now, as you keep scrolling over here to the right, okay, in order to work the magic to make these histograms automatically update as we change the numbers, I had to do a little bit of Excel magic over here. Now, I'm not going to expect you to know how to do any of this that you see here, and as I actually say, don't alter these formulas because this is the magic behind the curtain that is creating these histograms. So just leave this here as it is, don't move it, don't change it, and everything will work out perfectly. Okay, so first things first, if we take a look at the data here, to keep the amount of numbers fairly small, this is a fairly small subset of numbers. It's meant to represent a sample of a larger population. And we'll talk about distributions in a later lecture, but this is a sort of typical distribution that I'm sure everybody has seen before, sort of bell-shaped curve. We often look at this when we're thinking about grade distributions in a class, and this is what we call the normal distribution. So when we get to the later section where we're looking at this column y, we will alter this distribution a little bit and see what happens to some of the values for the descriptive stats. Now, we could have used more continuous numbers with decimal places, but you'll notice that I kept things fairly simple over here using just whole numbers. And by doing this, we're able to see, looking over here on the histogram, you know, this bar represents the number of 5s, the number of 6s, number of 7s, 8s, 9s, 10s, 11s, etc. All right, so what we're going to do here is calculate some of our descriptive statistics. So just so it's clear what the headers are, I'm just going to bold this column. All right, so when we first went to calculate mean, so Excel doesn't have a formula called mean. They have average in Excel. So remember your formula making skills. Here we will enter equals average, and as you start typing it, you see it pop up. If you see one you like, you can hit tab. And then for average, now we just have to enter the range. So we could type it in, or we could click over here on A4 and drag it down to A23 because that is the range of our data. Enter, and now we get 7.95 is our mean. I'm just going to center these. So 7.95. And if we look at this first plot up here, this histogram, now we see a red line show up showing the mean. And as we calculate mean and mode, you'll see other lines pop up on this graph. I won't really talk about them now. We'll talk about them a little bit more later when we start looking at different distributions. So median, this one is also a fairly easy formula in Excel. Most of these formulas that we're going to talk about today are fairly easy. So here again, we can click and drag to get our formula. Just to make things a little bit simpler, I'm going to come up here and I'm going to select the parentheses and the range. I'm just going to copy that so that when I write these later formulas, I could just paste that in as the range. Okay, and we see that is 8. Now, mode is a formula that's been around since the beginning of Excel. It used to be just a simple equals mode, but now there are two newer forms of this equation in Excel. So as I start to type in mode, you will see them. So there's a mode multi and a mode single, you see, and it calls the old version of this formula, which is just mode, a compatibility function now. So let's go ahead and use mode single, because mode single is equivalent to the old mode function. And what this is going to do is just going to give us a single mode. So the mode is the value that is found most often. So if we look over on the plot, we see that we have more 8s than anything else. So 8 would be the mode. If we had multiple modes in our data set, single would only tell us the first mode. I'm going to avoid using multi, though, because these data only have a single mode. And also you have to be using what's called an array formula, and that's a bit more complicated than I want to get today. All right, so I just typed in equals mode.sngl and pasted our range in there, and you can see over on the side here, it's highlighted all of our range, so hit enter. And as expected, that's going to be 8 as well. Okay. You can find these formulas, the Excel versions of these formulas, on the handout that goes along with this week's module. All right, now we're going to now calculate the minimum and the maximum. Minimum is another nice easy formula, so just equals min, and then we can paste in. It's very handy if you copy that range and then you can just paste that in. And maximum is just equals max. Okay, so we have 5 and 11 as our minimum and maximum. And now we want to calculate a less common one. So most of you have probably heard of mean, median, and mode. But now I want to go ahead and calculate the first and the third quartiles. So we'll talk more in lecture about what these values represent. Here I'd just like to talk about the nitty-gritty of how you calculate them. All right, so the formula for quartile, you always have to type equal, remember, so equals quartile. As we start typing it, we see it pop up. There is an exclusive and an inclusive, and there's also, you see the compatibility function. Let's go ahead and, unless you have some really good reason for using exclusive, which we can read more in the help file about the difference between these if you're really interested. All we're really going to calculate are the inclusive quartiles. So let's go ahead and hit that. And then we need to, if we just paste our range in there, see it pasted it in parentheses. Okay? We don't really need those extra parentheses. Okay, if we go here, but we do see based on this formula here, quartile.inc, we need the array, and then we need which quartile. So this is supposed to be the first quartile, so we'll enter a 1. And you can see I have those extra parentheses there. It's going to calculate that quartile. And then if we go in, just to show you that those extra parentheses that we really didn't need don't do anything, now we see that. All right, now we can just copy this formula down. So copy, and we're going to paste that formula down. Now a couple things happen there, and there are more efficient ways to do this than what I just did, but inevitably lots of you are going to do it that way. So I just want to point this out. So we're going to change this to 3 because we want the third, but also when I copied that formula down, it moved our range. Okay, so see, now we're excluding this first 6 and we have an empty cell there. The empty cell isn't really going to cause any problems, but not including that first data cell is going to cause a problem. Okay, so equals quartile.inc, A4 to A23, and 3 because we want the third quartile. Okay, so we've got 7 and 9 for our first and third quartile. Okay, now let's calculate some other values here that help look at dispersion. So here we have range, then we'll calculate interquartile range, variance, standard deviation, all right, so here, range. Now, some people, you might see them indicate range as, sort of lower number to higher number, but that's not really what we mean by range. For range, we want a single number, okay, and range is simply the maximum minus the minimum value. Okay, so that's our range. And then the interquartile range, remember that the interquartile range is a measure of the data, and this is a measure of the range from the first to the third quartile. So it's a measure of the central 50% of the data. So interquartile range is simply going to be the third quartile minus the first quartile. So we see a range of 6 and an interquartile range of 2. And for variance, this is the first of our Excel equations where we have to remember that there is a sample and a population method for calculating some of these parameters. Remember, because a sample is a subset of a population, you're going to see some differences between the calculation of some of these values. So here we see there's a var.p and a var.s, and we're calculating the sample variance, so we want var.s, okay? And then we need our range. Okay? Now, just to show you that there's really just a little bit of difference here. So variance, if we calculate it for the sample, is 2.05. And if we come in here and we change this to p, okay, notice that it's 1.9. So it's slightly smaller when we're calculating for the population, and the reason why we see this difference is due to what is in the denominator. Okay, so either n or n minus 1. So we're going to hit undo up here so that we can go back and verify we are using the correct sample version of this. All right, so standard deviation here, we'll just start typing standard deviation. Now you notice there's several different versions of standard deviation here, as well as some compatibility functions. Nicely, if you just type in STDEV, it's going to give you the sample standard deviation. But let's try and use the more modern versions of these formulas. So we'll want STDEV.S, that's standard deviation of our sample. And again, we want our range. You could copy that in, you could drag, whichever way works best for you. Okay, so now we have our variance and we have our standard deviation. And now usually you're going to already know what your sample size is, but it's always good to double check in your data to make sure that it is what you think it's supposed to be. So we calculate n, and we simply do this using count. Okay? So count, and then I'm going to hit, actually, I'll just drag because I copied something else in there. All right, so out of 20, I knew that I gave you 20 numbers, but this is a handy check on that. Okay, so the next one, CV, this stands for coefficient of variation. And coefficient of variation is just the standard deviation. So we can go standard deviation divided by the mean. And you see this is a fraction. Usually coefficient of variation, though, is represented as a percentage. So I'm going to go ahead and put parentheses in here and multiply this by 100 so that we have it in its more common form. So we've got an 18% coefficient of variation here. And because this is standard deviation divided by the mean, essentially what we're doing is scaling the mean. All right, so we've got our coefficient of variation. Another one that is used far less often is called mean deviation. So mean deviation, the equation for that, remember, because Excel doesn't have a mean function to get the mean, the formula for that is average. So it's actually, you start typing average, so avdev gets us the mean deviation. Okay, and remember there are multiple ways to do this. Okay, we could just type in A4 to A23. We could copy, paste it, we could drag to select that range. But here's our mean deviation. Okay. Sum of squares is another one that we have talked a little bit about. And, well, depending on when you do this, we've either talked about it or you've read about it, and we will talk about it. Sum of squares is a calculation that we will be doing in lecture. We'll probably do a little bit of this on lecture exams. It was definitely far more important calculating this when all of these calculations were done by hand. All right, but it's good for you to know what this is. So the sum of squares, to get Excel to calculate this for you, this is deviate squared right here. Okay, and then again, we need to get all of our numbers in here. You could select a range where your numbers are, or if you notice where it says number 1, number 2, ... you could enter a string of numbers in here. That's going to be quite time consuming, so I don't really recommend that you do that ever. Just select your range where you have your values, but that's another way that you could do it. Okay, so here, the sum of squares, we see a value of 38.95. And just to remind you, so if we think about what sum of squares divided by n minus 1 is, if you remember, sum of squares divided by n minus 1 gives you variance. So just to verify that, okay, if we do sum of squares divided by n minus 1, notice that we get 2.05, which is the exact value for our variance. So really that was just to verify to you that this is how we calculate variance here. So I'm going to go ahead and delete that right there. Okay, now one thing, actually let me pull this back here for a moment. Most of you probably already know this, but you want to make sure that your mathematical operations are going to happen in the right order. So in order to make sure that your mathematical operations happen in the right order, we use parentheses in Excel. So if you notice here, I used parentheses around this n minus 1 because I want n minus 1, the 20, because that's n, minus 1 to happen before the division takes place. Okay. Otherwise, if I just wrote E24 divided by E18 minus 1 without the parentheses, it would first divide E24 by E18, and then it would subtract 1 from that value. So that's not what we want to calculate. We want to do n minus 1 first. So make liberal use of parentheses. If you remember your basic rules from mathematics, you know that power functions are going to happen first. They're going to move left to right. Then any multiplication or division functions are going to happen. And then finally any addition or subtraction functions are going to happen in this equation that you've written. So if you want to just be sure that the operations are happening in the manner that you want them to happen, make sure that you use parentheses. So you'll see in my equations I tend to use more parentheses sometimes than are necessary, and that's simply to make sure that I don't end up with any errors based on mathematical operations happening before I want them to. All right, so one of the things that you will notice if you look at this plot on the top here, you'll see that the mean, which is 7.95, the median, which is 8, and the mode, which is also 8, they pretty much are all stacked on top of each other in the same place. Okay? And the reason why they're all stacked on top of each other in the same place is because they're all very similar. This is a relatively symmetrical data set. Okay? And what I'd like to do now is take a look at what would happen if we made this data set not symmetrical. All right, so what I'm going to do is I'm going to copy, or first let's go ahead and sort. Okay? So going to select these data, you go up to data and sort. Here, because I've only selected part of the data, I've gotten this pop-up error box. We just want to continue with the current selection because I just want to sort those cells. Okay? And we want to sort, we'll tell it we do not have a header, and we want to sort by column A, smallest to largest, that's fine. And the reason why I've sorted these data is it's going to make it a little bit easier for us to mess around with the numbers at the extreme so that we can alter that distribution. Okay, so we have the same numbers over here, and when I do that, you see, voila, we have a histogram pop up down bottom. And then the other thing that I want to go ahead and do, because here we have all of the equations for calculating these descriptive statistics for column A, where we have our x values, I'm just going to select this and drag it to the side. We're just going to copy it. And you see that we have an exact copy of all of the values because column B is exactly the same. But if you just randomly selected any one of them, you see that we're now referring to column B. Okay, so now let's go ahead and take a look at what happens when we start to alter some of these numbers. So if we go to the maximum value that we have, 11, and we change that to 21. Okay? And just to make it clear what I have changed, I'm going to go ahead and color that red. This is really just so that you can see this as you're watching the video a little bit clearer. Okay, so now we had a value that was at 11 up here. We moved that 11 over to 21. Okay, when we did that, notice that the mean, this red line here, it scooted to the right. It got just a little bit higher when we made that one little change. Okay, so now our mean is 8.45 instead of 7.95. The median stays the same because the median is simply the central value, and that hasn't changed. The mode is still 8 because 8 is still the most common value. And minimum didn't change. The maximum clearly changed because that is what we altered. But if you look at here, okay, the interquartile range didn't change very much. Okay, well, it actually didn't change at all. But if you look at the variance, so if you look at variance and you look at standard deviation here, we did have a variance of 2.05 previously. Now variance has jumped up to about 10.3. Standard deviation also, we were at 1.4, now we're at 3.2. So you can see that even simply changing a single value in your data set, in this case we changed an 11 to a 21, that's going to drastically alter your values for variance and your values for standard deviation. You can also see down here with coefficient of variation, that changed quite a bit even with just that single change. And sum of squares also changed quite a bit. So these measures of dispersion or variance within the data, the measures of spread in the data, we can see that they are doing a really good job of indicating to us that we do have greater spread in the data down bottom than we have up top. All right, so at this point, if these were your data, you would actually want to take a good look at this data point, because this data point at 21, which is so much different than all of the rest of the data, you'd want to examine that a little bit more heavily to make sure that that wasn't some sort of an outlier in your data set. All right, so now what I'd like to do is just sort of go in here, starting at this far end here, and just start slowly changing these values, okay? And seeing what happens as we change them. You can see that variance and standard deviation are continually creeping up, as is coefficient of variation and sum of squares. Here you see the mean deviation is starting to increase, but we still haven't seen a change in interquartile range. Median and mode are still exactly the same. Okay, so we're just going to keep changing, keep making this distribution more and more non-normal. Okay, so now once we hit 17 here, now we see a difference in that interquartile range. So we see it jump from 2 to 4, and we're starting to see the mean scoot even further over to the right. And really the mean kind of represents the middle balancing point of your data. And that's really easiest to see looking at a graph like this, because you see that this mean is going to act sort of a balancing point. If you think of the values over here and the values over here as weights, the mean is going to be that middle point where the data would balance. All right, so if we just keep changing these numbers a little bit, keep altering our data here, okay. Notice as we do this, okay, now once we get to 13 here, we can start to see some separation between the median and the mode, because you can see these 8s over here, we've started to overwrite a little bit. You start to see these measures of central tendency are starting to spread out more and more. Okay, and if we just go in here, change yet another one to 12, and as I do that, watch down here what happens to these values. Okay, you can see now the median jumps way over to the right here. Okay, this is just showing you red for the things that I've changed in this data set, and I'll bold them just so that they pop. All right, so looking at this, you can keep playing around with the numbers, and I would recommend that you keep this file so that you can mess around with these numbers a little here and there, just so that you can get a better sense of how mean, median, mode are all related to each other, and what happens with these measures of dispersion over here. But if you look at this bottom plot, what we're seeing here is what we call a right-skewed distribution. Right-skewed because if we look at this distribution, the tail over here, the right-hand tail, is extending far longer than we would expect based on a normal distribution. So what we see when there is a right-skewed or a right skew to our data, we see that the mean is going to be the highest value, because these high values over here in this right-hand tail pull that mean up higher. Then your central value, the median, is going to come next, and then the mode. So with a right-skewed data, if we go from sort of left to right, we have mode, median, mean. Now, if we were to alter this distribution, just come up here and play around with the numbers and make it a left skew, you would see the opposite pattern, where you would see mean, median, mode. Okay? So keep this file, play around with these values in here so that you can get a good feeling for how mean, median, mode are all related. If you have a normally distributed data set like we do up here, you don't have any significant right or left skew, you don't have any big outliers anywhere, you would expect to see a pattern like this, where the mean, the median, and the mode really do all appear in roughly the same place in your data set. Okay, so at this point, that was the description of how we would calculate some of these descriptive statistics here for some numerical data. And now what I'd like to do is come down here to the other worksheet that I've given you. This worksheet shows you some categorical data. In this case, these are simply some made-up data, imagining that we have 3 different ponds, and we went out into those ponds and we counted up the number of turtles that we pulled out from the ponds. So here you have the species of turtles: painted turtles, red-eared sliders, stinkpots, common map turtles, red-bellied turtles, and alligator snapping turtles. And because this is a made-up data set, I was able to keep the numbers the same. So the total numbers, if we look here, and we'll actually go ahead and just count up the total. So equals sum for our range there, and then we can copy this across. So you see that the total here is the same in each of the ponds, but you can see that I have altered, I'll go ahead and make this a little bit bigger, you can see that I have altered the evenness, the proportion of numbers of different species here. And the first thing that we're going to do is calculate some basic statistics, essentially the proportions in each category from this total. So this is something very similar to what we've already done, just calculating relative frequencies. But then we're going to calculate these indices that you read a little bit about in the supplemental material. And these equations are just here for reference. So we have the Simpsons index and we have the Shannon-Wiener index. And I just want to go through how to calculate these because we don't have a nice, simple, easy Excel formula for how to calculate these. It involves a couple different steps. All right, so here we can see that these total numbers are the same. And what I'm going to do is just copy this. And I'm going to paste it down here simply because I would like to have all those headings in place for calculating our relative frequencies. All right, so we want to calculate our relative frequencies, and we've done this before, but just to sort of walk through these steps, okay? B4 would be the value that we want in our numerator, and we want to divide that by the total, okay, which is found here in B10, but we always want to divide by B10. So we stick that money sign in there, and this is always going to divide by B10. Okay, we can now copy this down, and we can also copy those across. And we have quite a few significant digits here, so we can reduce this a little bit. Okay, and here you can see that in each case, all of these frequencies add up to 1. This is exactly what we're expecting to happen, so this is just yet another check that yes, we're doing things correctly here. At this point, when we calculate the Shannon-Wiener index, these zeros are actually going to be a problem, so I'm just going to delete those out. But in doing so, you can see this doesn't affect the total of 1, of course, because they were simply 0. Okay, so we have our relative frequencies now, and now we're going to go ahead and calculate these indices. So if we look over here first, okay, we'll calculate the Simpsons index first. And if you look at these equations and you compare this back to what you saw in the notes, this right here, this is the version, or rather this, d is equal to 1 minus the sum of this here. This is what I put in the supplemental notes. This is the way the formula is typically represented. But if you remember your fractions and your basic math skills, this over here is equivalent to this over here. More specifically, because both have the 1 minus portion, this is equivalent to this. And really the only difference is what's happening in the denominator down here. And if you look here, this would be the equivalent over here of essentially saying summing up 1/3 plus 1/3. Well, you know that's going to be 2/3. And then over here, what we would be looking at here is more looking at summing up 1 plus 1 and dividing that by 3, which again, 1 plus 1 divided by 3, that is again going to be 2/3. So these are equivalent. All right, so if we come over here, and I already have Simpsons index written here, so I'm just going to copy that over. Okay, so here we want to calculate Simpsons index, and I'm just going to copy these over as well because we need values for each one of the pawns. And then if we look at what our equation is, okay, we're going to need n times n minus 1. Okay, and the reason, let me backtrack for just a moment, the reason why I have this version of the equation over here is because that makes the portions of this equation a bit easier to calculate in Excel. Okay, it just makes it a little bit easier math for calculating in Excel. So what we want to calculate is this n times n minus 1. Okay, so technically all of these are going to be n times n minus 1 values. This would be n1 times n1 minus 1. This would be n2 times n2 minus 1, and so on. Okay, but if we click in here, okay, this is going to be equal to our raw counts over here, n times n minus 1. Okay, and that gives us 870, and we can copy this down all the way for each species and copy it to the right as well. And then we can go ahead and calculate our numerator total. Okay, so our numerator total is simply going to be, I'm actually just going to copy this, okay, because we can just copy that over. Each one of those is simply getting the sum of the same number of numbers above it. So here we see the numerator total for each of our ponds, and then we can calculate our denominator. Okay, so remember the denominator total is simply n, big N, times n minus 1. Okay, so here, B10, the total of all of your numbers here added up, times B10 minus 1, that is big N times big N minus 1. Okay, and we can copy that to the side. Okay, and big N times big N minus 1, the denominator should be the same across the board. Why should it be the same across the board? Well, it should be the same across the board because we have the same total. This was on purpose. This is not typically what you would find in nature, but this is what we find because I made up these data so that we could clearly see some differences between these three ponds when we calculate the index value. Okay, so to calculate the index value, okay, that is simply 1 minus numerator over denominator. Okay, so equals 1 minus, and then I'm going to use my parentheses again. Okay, numerator divided by denominator. Okay, and if we go ahead and decrease our number of significant digits just a little bit to make that a little bit easier to deal with, and we can copy that over to the side. All right, so now what we see are three different index values. Okay, and in seeing these different index values, if I just blow this up a little bit here, we see that they are increasing from pond 1 to pond 3. Now, if you think back to what the Simpsons index tells us, the Simpsons index ranges from 0 to 1, and as you get closer to 1 with the Simpsons index value, that tells you that there are more categories and or the data are more evenly distributed among those categories. So if we look here, pond 3, remember pond 3 only had 3 species, okay? Only had painted turtles, red-eared sliders, and stink pots. And they also weren't incredibly evenly distributed either. And we have an index value of 0.4651. Now, if we move to ponds 2 and 3, well, ponds 2 and 3 all had 6 species each, and they have the same number of species between pond 2 and 3, but if you look at pond 3 is more evenly spaced. So we would expect to see higher index value in pond 3, and in fact that is what we see there. All right, so that's Simpson's index, and the other index value that we want to calculate is this Shannon-Wiener index. Okay, so if we calculate the Shannon-Wiener index, again, I'm going to copy over the pond names. Okay, and Shannon-Wiener index, you see here, H is equal to negative, we just take the negative at the end, the sum times the relative frequency multiplied by the natural log of relative frequency. Okay, so to calculate each of these values, and then we will sum them up. Okay, so here it's equal to the relative frequency multiplied by, and I'll use another parentheses here, ln is natural log in Excel, and we want the natural log of that same frequency. Close parenthesis around that B17, close parenthesis for the ln B17. Okay, and this gives us a negative value. Okay, all of these, in fact, are going to be negative. Okay, and because they're all negative, when we sum them up, we're going to have a negative value. That's why we take a negative at the very end. Now, remember why we have these errors showing up here? We have these errors showing up here because we don't have anything over here. We deleted those zeros in here because they would cause a problem. Just to see what I mean, because if we enter 0 here, we still have a problem over here because taking the natural log of 0. But I'll keep it there for just a moment so that we can copy it over. And now go ahead and delete those. Okay, we're going to need the total, so I'm just going to copy our total from over here. Okay, we have our total values. Now the index, remember I was just speaking about how we have negative values, and the index, we just need to take the negative of that. So you could equal -1 times this value, or you could just equal negative and then enter your cell reference. Okay, so now we can copy that over to the side, and again we have lots of decimal places here, so let's just take that down to something a little bit more reasonable. And you don't have to do this. I keep centering things and making them bold in this data file as we go through. Really, the reason that I'm doing that is just to make it stand out a little bit easier for you as you are looking at this video tutorial. Alright, so looking at the Shannon-Wiener index here, we see values ranging from 0.78 up to 1.8 here for pond 3. So we see that the index is increasing from pond 1 to pond 2 to pond 3. As we get more species in the index, the index is increasing. And we know that pond 2 and pond 3 both have 6 species in them, but we also see an increase in the index as evenness increases. And as we discussed before, the evenness in pond 3 is greater than in pond 2. So we see the pattern that we would expect to see, and this is the specific reason why when I created these data, I made sure that we had the same number in each. So we can look at what happens to the change in the index when we have differing numbers of species, even if the total number of individuals is the same. Alright, so if we just backtrack a little bit, okay, we've gone through how to calculate the Simpson's index, how to calculate the Shannon-Wiener index. Okay. What are these really telling us? Okay. Well, if we look at the Simpson's index, what this is really telling us is if we were to draw 2 turtles at random, the chance that they would be different. Okay. So if we look at these index values here for the Simpson's index, you see that in pond 1, if we were to randomly draw 2 turtles from this pond, there's only a 47% chance that they would be different. But in pond 3, where we know that we have 6 species and they're more evenly distributed, in pond 6, there's an 85% chance that if we were to randomly draw 2 turtles out of pond 3, they would be different species. Okay. Now, this doesn't have to be species. Okay. I keep referring back to species because in this example, we were using species, and also these indices are used most frequently when you're talking about species, but it could be any categories here. Okay, so that was the Simpson's index. Now, if we look at the Shannon-Wiener index and what that is telling us, it's telling us something similar, but a little bit different. So the Shannon-Wiener index is looking at how difficult it is to know what species you're going to get if you drew one out at random. Now, as we talked about in the reading, there's no upper limit with this index, but we can see that as we move from pond 1 to pond 2 to pond 3, we are having a greater chance of knowing what we would get if we drew at random in pond 1, because the lower values indicate that you're going to have greater certainty of knowing what you're going to get if you pulled one at random. Okay. There's no upper limit to this index. It doesn't have a set range like Simpson's index does. Remember, Simpson's index is going to range from 0 to 1. Shannon Wiener index, there's no upper limit, but in these kinds of studies where you're looking at numbers of species and species diversity, typically about 5 is the highest that you'll probably ever see in these types of things. All right, so we've worked through how to calculate the two indices and also how to calculate relative frequencies for categorical data. Looking back at our numeric data, we looked at how to calculate these values of descriptive statistics, things that are going to tell us a little bit of something about the central tendency of our data, as well as the spread of our data, and took a little look here of what happens if you alter the distribution of your data. All right, so that concludes things for this tutorial on descriptive statistics.